So welcome to our first session on the C++ course. So this is an introductory session that should familiarize you with the content. More of the actual programming will then come in subsequent sessions. You see we have a long list of people involved in this. The list is likely not complete, so you're going to see different people throughout. So the first question we should ask is, what is actually a computer? Okay, and this is a funny thing to think about, because originally that title had been a job title for humans. Okay, so it was you've probably seen, if you have seen the movie Hidden Figures or things like that, you still see that the title human or computer was a job title used for people who calculate something, they compute something, and that really has then changed later on. So this is actually, there were a couple of people who who thought about, okay, certain calculations like adding, multiplication, division, doing all these arithmetics, they could also be done by a machine rather than by a human person, because the machine might be way faster, which originally, by the way, they weren't. So they said, okay, let's build a machine, and the first machines that we saw were electromechanical. So when you went into a room with a computer, it was more like a factory with things flipping and turning around and you're spinning, rather than what we have today as a computer on a laptop. Okay, so it was an electromechanical device. There's different parallel developments. Probably the first one and most influential one was SUSE, who built a computer called Z1 and then Z2, and then Z3 was the first electromechanical one. So he's kind of, if you want, the inventor of the computer. That was in 1941, and you realize that he couldn't continue that work due to the war. Okay, but he was the person who invented that kind of machinery. If you ever have the opportunity to travel to Munich, there's a technical museum there along the river where you can still see the Z3 in operation. You can see how things flip. So it's quite interesting. All right, now these machines were huge. They were extremely slow, difficult to handle, very expensive. So people switched and later on made, okay, can we do that? Can we do that electronic transistors replace all the things that swap for them back? Okay, so we went from a job title, which is more of what is to be done, all the way to more of how are things done. So the term has seen a certain semantic shift. Okay, and you see here one of the, again, if you like movies, and if you have seen the John von Neumann documentary, you might heard the term Bletchley Park. That was about encryption and deciphering in World War II. That was where we saw one of the first electronic devices called Colossus in 1943. By the way, I think Elon Musk has an AI machine which he called Colossus, but he stole the name. Okay, so it's not an original invention. Okay. So, what is a computer? And there is quite a seminal paper. It's actually, he called it a draft. And that is by someone we will meet over and over and over again today. And that is John von Neumann. Okay, so he was actually born as János Lajos. Okay, so he's from Hungary, in Budapest in 1903, and then again due to he had to emigrate to the United States, where he died in 1957, and he worked at different places. But the important thing is that in 45 he wrote that paper, that report on a computer, and he said this is what a computer should look like. And again, you can argue, because there were a couple of people who had similar ideas, but this was the influential one, and that name did stick. Okay, but that happens frequently in science. Okay, John von Neumann, and now let's have a look what he said what a computer should look like. Okay, and you can think of a computer in a very, very simple way, you can think of it almost like three people or a couple of people working together. So at the core of a computer is someone sitting at a desk. Okay? And that is a very primitive desk because it can only host a couple of sheets and each having one number. So a very, very simple thing, okay? Let's assume there's probably only 2 sheets and we call those things registers. And this is the guy we call ALU for arithmetic logic unit. What that person can do is compare one sheet to the other. Are they the same? Is one number written on one of these sheets bigger than the other? This person can sum up 2 sheets. So if there's a 3 here and a 4 there, okay, 3 plus 4 should be 7, okay? And then write it instead, erase one of the numbers and write the 7 in there. So that is everything an ALU can do. Okay, so you don't get anywhere with 2 sheets of paper. Okay, so we have something else. We have something like a memory, which is like kind of a library with just a lot of these sheets of papers in that analogy, a lot of these sheets of papers in a row, and they are enumerated. Okay? And now you can think, oh, here's the desk, and then there is a library, maybe in a building somewhere over there. So we need something in between, and that is called a bus. So those are the 3. In the von Neumann thing, there is also something like control unit, which issues instructions. So actually we have 4 different ingredients. So that is important to keep in mind, but those are the 3 we have to really think about, because often the control unit and the ALU are taken as one unity. But originally they kept it separately. Okay, so let's reiterate. We have the processor, which we call a processor, but in the original thing there is a control unit, which is not depicted here, and this arithmetic logical unit, and that thing can really do only very simple operations, unary and binary, like adding something, incrementing +1, comparing. So very simple. So all it does, it takes 1 or 2 numbers, combines them and writes the results again into one of these local sheets of paper on the desk. And there's a very small number of these desks. It also has a program counter. We will see that in a minute, but that's just we can think of that as just another sheet. Indeed, it is exactly this. Okay, and this is just a number, and we will see what the role this number plays. All right, then we have the memory, which is like a huge enumerated blackboard, or whatever you would call it, okay, with lots of sheets. And basically everything it can do is accepts or delivers one number at a time. Okay, so now let's do an example. What does that mean? We want to compute A transpose B, which is a scalar product, which we will need all the time in the scientific computing, machine learning. That is kind of one of the simplest thing. So we have 2 vectors, A and B, okay, with different entries, and we want to compute A1 times B1 plus A2 times B2 plus A3 times B3 and so forth, scalar product. Okay, how does a computer compute? So computer in the sense of a machine, how does a computer compute a scalar product? So conceptually, we have here the ALU. The ALU tells the memory, give me A1. Then the first value goes from memory into the register. Then the computer says, the control unit, memory, I need the B1. The B1 goes into that register. Now I have A1 and B1. Now I can call the ALU, can you please multiply the 2 of them? We compute A1 times B1. The result is written into a register. And then we can, for example, because we need those 2 sheets for the A2 times B2, we can say, okay, I now have the first result, partial result. Boss, can you please move that value back into the memory somewhere? I'm gonna need it later on. And then we continue. So a computer is extremely primitive in that sense. Okay? Take one, move the data over here, compute something, move it back, and it goes like this, forth and back. All right, this is kind of another sketch. This is what von Neumann basically said. He said, okay, there's a control unit, which is kind of the mastermind of the whole thing. There is this arithmetic logic unit. That is what you find if you unscrew your computer or your laptop. This is what you would call the processor nowadays. They're in there. We have here these registers. We have a bus, and we have the memory. These are kinds of the four ingredients. Morning. These are the four ingredients in the original von Neumann architecture, and that is all what a computer can do, and the bus connects everything. You might ask, yeah, well, but I have a mouse and a keyboard and a screen. They all plug here into the bus. So we speak about that thing here. Okay. So that is the von Neumann architecture. Now let's have a look how this exactly works with the memory. So I've said the memory is just a huge sequence of numbers enumerated from 0 to, quite a lot. Depends on how much memory you have. Okay, and now the interesting thing about the von Neumann architecture is it also holds the instruction stream. So a computer program is nothing but a sequence of numbers, and the numbers mean do something, okay? And that's an instruction code. So the 20 might mean move something, the 30 might mean add something. It's an instruction stream. So what we have is really, we have the main memory and the computer program. When you start your application, the first thing that happens is that this computer program is moved into your memory. Okay, so now it's here somewhere in the memory. And then the second thing is, I said we have here a special register, a special value, which we call the program counter. So we move the program into the main memory and we set the program counter to the very first instruction in there. Okay? So here in my sketch, we load add into this small program here, we load that into memory location 113. Next thing is we set the program counter to 113, and now the show starts. Now the computer starts to compute. And what it does is, okay, program counter 113. So first of all, the control unit tells the memory, can I have whatever is written at 113? And the bus gives back a certain number, and that is the code for add something. Okay? So we add something, then this is incremented, 114. We get the next one, so add, and then this is an address. Add whatever is written on 24. Then we increment once more, and what is written at memory location 25, and then we load once more, and store the result at memory location 21. So this is how we run through an application, okay? Very, very simplistic. Okay, so what happens here? We read that out, add whatever is written at 24. So next thing the control unit does, it issues again a command. Can you please give me the value stored at 24? That goes into one of the registers of the ALU. Give me the value that's written at memory location 5. That goes into the register. Add the two of them, write them to 21. So we should end up here with a 9. So it is that simple. There's a few things to see here immediately which are interesting now historically. So in the von Neumann concept, and it's different to a machine, for example, developed around the same time in Harvard, and also to the SUSE machine. The actual code is also in the memory. This is the reason why you have a lot of ransomware, viruses, all of these things. Because what obviously can happen in theory is that someone modifies on the fly what is written in the memory. Okay? And this is what a security breach means. This is what you get when you have a virus on your computer. It on the fly changes here the program. And in this way it can inject, that's what where the name also comes from. This is how you can inject new code into an existing code. Okay? Other machines, the Harvard machine, the SUSE machine, kept the part where you store the instruction scheme and the data completely separate. They do not have this intrinsic security problem in there. Anyway, we're not talking about security, we're talking about see how we want to get there. Okay, so we've said that control unit has the program counter that is incremented every now and then, so we run through the instruction, and basically that way we can read a program from the memory. Okay, it's not hardwired anymore, it is programmable. We spoke about the ALU. Very simple, it can do the calculations. Originally it was completely separated, then it was integrated into the processor. We will see later in this course again a development where it is now again separated from the CPU. You could read a GPU as kind of a very advanced one, then it's completely separate. So things move forward and back, okay? But in principle, that is where the heavy lifting is done in terms of computations. And we've done that. Okay. All right, so now let's have a look why we don't want that. Why this is quite annoying for us as a user, this whole machine. Because what exactly these numbers here mean and what type of operations a processor allows you to do, it depends on the machine. Okay? So if you have a Mac machine, it supports different instructions here. If you have an x86, if you have an ARM machine, like on your smartphone, or on one of the big AI clusters, it's different codes that are supported here. If you do a RISC-V architecture, that's a big, it's a new architecture, not new architecture, but an alternative architecture, again, completely different numbers. To make things worse, even if you have a machine, a chip from the same vendor, okay, so you have 4 generations of Intel processors, with every new generation, a different instruction set here is supported. So that's annoying, okay? Because for every different thing, it is machine specific. Constraints as well. Sometimes you cannot combine them in certain orders. And the performance of the command is also machine specific, okay? Sometimes certain combinations and certain instructions need quite long, and others are very, very fast. So originally, you had programmers with these huge books on their table, and they had to sit down and had to look up, oh, I want to do an addition, that is this number, and they puzzled together the application like this. Now it's very obvious. And there's one more thing. You also needed a big sheet of paper where you kept track where in memory your data resides. Okay? So originally programming was really like looking through these big books, looking up program codes. I need an addition, and then you looked up into your sheet or whiteboard and I have space here, so this value should go here and this value should go over there. And this is how you wrote programs originally. And we already said, it's cumbersome, it's very slow, it's error prone, try to find an error in such a code. And it's not portable because once you get a new machine, you have basically to start from scratch. So that was what programmers did originally. And the conclusion is, nowadays it seems to be extremely clear, but wasn't at the time. We need something that is more abstract, a description that allows us to streamline this process. We can't work like that. But it is important to know what is happening under the hood, because we will now build up these abstractions, and then later throughout the course and the whole your program, you have to go back to this at one point to understand why certain things are happening the way they are. Now, we said this is how, now we've kind of revisited. You probably knew all of that, isn't it, with von Neumann? Did you hear about von Neumann before? A little bit. Have you heard about von Neumann and that idea, how a computer is organized? So, okay. So, some aspects were known. So anyway, my point is, this is not how we want to handle a computer. So let's have a look what happened next. So this is kind of a history lesson to a certain degree so far. We're going to continue with that, and we're going to continue with this lovely lady here. This is Grace Hopper, okay? And she was an absolute pioneer in computer science, and that is the reason if you look at some of the biggest supercomputers at the moment in the world, so for example the Alps supercomputer in Switzerland, in the UK we have the Isambard AI system, those are all built or have feature NVIDIA technology. Have you ever looked what the chip is called? The chip is called Grace Hopper. Okay, so that's the reason. So at the moment, the big AI machines are named the NVIDIA machine. The flagship is called Grace Hopper. So Grace is the CPU and Hopper is the GPU. Okay, so far everything we have discussed is something we can describe as assembler code. Okay, so we can write down in a code. We can write down at 24, 25. Store at 21. We don't have to write down only numbers, okay? We can use words to describe that and then kind of automatically do a text replacement system so it's numbers. But this is not how we want to do that because that's kind of machine-ish code, so machine specific. We discussed that. And kind of her contribution is that she was the first to flag that's not the way we should do things. Okay? And she introduced that theory of machine-independent programming languages, and all that means is I want to write down my code once, and then I want the machine to do that tedious translating it into the right code sequence. This is nothing a human should do because it's quite mechanical and there's too many errors and it's too slow. And she came up with a language that's called COBOL. I don't know whether you've heard about that, but it's still used in the financial sector, not so much at universities, but there is still a couple of COBOL applications out there. So probably if you want to have a secure job, you learn that old language because someone has to maintain the software. But I don't think that is her major contribution. I think her major contribution is that she was really a pioneer around the compilers. And compiler is a name for a machine translator. We're going to define it a little bit now. So, this was her step. I want to write it down machine independently, and from there on things really took off. And then people started to continue along that. They said, oh, I don't want to think about numbers written on a sheet of paper in the ALU. I want to argue about types. Is it an integer number? Is it a floating point number? Is it a yes, no, a Boolean expression? People said, oh, I don't want to write down long sequences of do that, do that, do that, do that. I want to think of functions, okay? And we call, so people introduced functions. And then from there on, people took it one step further and said, I don't want to think in terms of functions, which is really call this, call that, do that. I want to think in terms of objects interacting with. And with each of these different ideas, people started to introduce new, more advanced programming languages, but this is really kind of the godfather of it all. And at the end of the day, it always has to feed into machine code because that is what our machines understand. Okay. By the way, that continued, okay? Later on, people started, this is all too heavyweight, we want to have something lightweight, use scripts. And then, the idea, things should be able to change their type. You see that in Python. People started to think more in web service way. Things are distributed and should communicate with each other, and so forth. The punchline is, all of these things can help us to improve our programmers' productivity. But you always have to keep in mind that you pay a price. Okay, it is expensive, and we come back to that later on. So it is very important to have this still in your head somewhere. We're going to work with these high abstraction levels, but at the end of the day, we have at least once to understand how it is broken down into these fundamental operations, and from there on, we can argue why codes perform in a certain way. So, a compiler. What does that mean? It really means what we write at the moment so far with machine code is something that we have here, okay? Move from memory location 4 that is wrong, to register A. Move from memory location 5 to register B, add register A and B, write the result into A, move register content A into memory location 24. So that is copy and paste here. Okay, so this is kind of the machine code that we have seen so far. But what we really want to do is we want to write things like a equals x plus 3. Okay, because that is kind of something we understand. This is something we don't understand, and we don't want to care about where in memory x is. We don't want to care whether it goes into register A or B or C or D. This is all stuff we don't want to care about. So we are searching for that. So we want to have a translator. It's literally like a translator who takes this and maps it onto this type of code. They're not the same here in this example, but in principle that is what we are up to. There's different types of that, and this is interesting to look at. So there is the algorithm. I shouldn't write algorithm here, I should write source code. That is the way how we write down things. And then we can take that and we can pipe it through the compiler, and it gives us something that is a machine code, and this is something we execute. Now let's have a look. This is what you have, for example, when you take your smartphone and you open the app. Somebody has written that app and has translated it into something that fits on your iPhone or fits onto your Android. So you have something that is already machine code, and then you execute it upon request because you issued. Same with a laptop, okay? You install an application. The application is already typically given you as machine code. You download it from somewhere, and then you double click on the symbol, which really means now you execute the application. So this is the very traditional compilation path. You can also do it differently. Have you done Python? Okay. If you do Python programming, it is a scripting language. Then you go like this. In Python, you have really the Python code per se. And then you type in Python and MyScript, Python MyScript, or you use a Jupyter notebook where you click. But really what this does is, there is the Python interpreter, which takes the thing and translates it on the fly into machine code and executes it immediately. At the end of the day, they both have to deliver the same thing because they both have to ensure that it runs on your particular machine. It's just here that it is done once, and you don't see the source code anymore. Actually, for example, that is what a lot of companies, Microsoft won't give you the source code for Windows. Okay, so you're never going to see that. You always will only see the machine code. With Python scripts, it's different. With Python scripts, you see the actual source code and you interpret it on the fly. And there is advantages and disadvantages, obviously. So for example, if you go down this route, what happens? The one person who wants to distribute their application, they have to translate that for every single system that they want to support. And if someone comes along and says, I have this particular system, but you have no executable for that, that means you can't give them your code. Here with the interpreter, it's very simple because it runs everywhere. The disadvantage maybe is maybe you don't want to hand out your code. Okay, if it's your business property, but also you can do a lot of optimizations. You can study your code in detail. Again, computers can do that for you and make a really, really fast one, because here, it's basically somebody has to read through your code line by line and then translate it, which is expensive, needs some time. Whereas here you do that once and then you are done. So compiled languages are typically significantly faster than interpreted languages. Not a surprise. There is an intermediate way. What you can do is you can create a compiler which creates something we call intermediate code, which is kind of an abstract machine-independent executable, but very, very low level, where a lot of the heavy lifting is already done. And then you can have an on-the-fly interpreter of that. If you ever used Java, that is the Java way. or C#. In Java, you would take your source code, Java code, and you would translate it into class files, which is something like an assembler that is not tied to a particular machine, but an abstract machine that the Java guys came up with. And then you can take that and you can, on the fly, and that is relatively fast, way faster than what you would do with Python. Okay, you would translate that. Okay. Yeah, term bytecode has different names. Intermediate code is more or less a synonym for abstract machine code. There's hybrid variants like this. There's also something like called Java Hotspot, which looks at particularly expensive routines and does that translation once and then keeps it in mind. You know, if you speak to a translator, translating, for example, if you ask someone to translate Harry Potter on the fly, okay, once they have done the one chapter, and if the next person says, can you translate me Harry Potter on the fly, they would chapter 5. Oh no, I've already done that before. I used the one that I've already translated. So that's kind of the hotspot virtual machine. It takes particularly things that are used over and over again, and when it has done that a couple of times, it says, well, wait a second, I translated once and then I reuse it. Yeah, and then there's still hybrids. So for example, we will likely see that in term 2 there is OpenCL for GPUs, which again doesn't do this here, but does something like this, where you translate, it's like the intermediate code and then it's translated to the particular GPU that you are working on the fly. So compiler and interpreter are probably the two important concepts that you have to keep in mind when you speak about translation processes. In C++, we always, well, traditionally always work here in the compiler area. And what we will do is we will break down this compilation step into multiple sub-steps. And you will see that there is some resemblance to that, to that thing there. We can draw the analogy later on. Okay, now before we do that, we have to study what type of what we want to achieve. But let me just quickly wrap that up. So what we want to do is we want to write things like A equals 4, B equals 5, C equals A plus B. And this is what should come out, okay? Move the 4, the constant, to memory location 24. Move a 5 to memory location 25, add memory location 24 and 25, and move the result to 21, which is then where implicitly C is stored. So we want to deploy all of that to the compiler, where the compiler knows at which memory locations A, B, and C are stored, and what operations we actually have available. Also, it should manage the program counter, and we can see that later on. We have some examples online, some movies where you can see how the program counter, for example, is used to do that for loops. Okay. Okay, this is something I want to close. When I studied, that was a saying, and I want to quote it. I've been told every real computer scientist has to invent at least one programming language throughout their career. Okay, so you can create them yourself. We're not going to do that here. We study C and C++, but this is still an active field of research where people create new languages, and the current trend at the moment is that a lot of people create domain-specific languages for particular application domains. Okay, so let's step back and let's quickly revisit and contemplate what kind of programming language we are searching for. Okay, and for this we do something completely different. So let's move the whole programming thing to the side, and let's quickly think what we want to achieve, and then we bring the two things together. So what we're interested in is science or insight. Okay, we want to have new insight in research, business, whatever. And how do we get insight? And have you ever heard of the urban legend of Galileo Galilei? He was standing on the Leaning Tower and he dropped two things. Why did he do that? Well, up to that point, people thought that the heavier object, the faster it falls down. So he climbed that. That's a legend. Okay, it hasn't happened, but it's a nice story. So according to that, he walked up to the Leaning Tower in Pisa and dropped two things of different weight. And then he looked. And what did he observe? Well, they hit the ground at the same time. So what does this tell you? Well, up to that point, people had a theory how things behave with gravity. The heavier something is, the faster it falls down. That was kind of the theory. Okay? And then he did an experiment and he said, no, this is not what we observe. So he had to go back to the theory and alter the theory. And this is really still how we get insight. Okay? So we have an idea what things look like. We try to look for an experiment or for data out there, and then we go back. Or we start from a phenomenon that we observe and we say, well, wait a second, that is not, I can't explain that. So it's an open question. Why is it like that? And then people go back and they make a theory, and this way they go forth and back. Okay? This is how science worked until 100 years ago. And now this breaks down. Why? Well, because you only get that far with theory. So nowadays, all the formula that we have, complex differential equations, we can't solve them anymore. We know that they have a solution. So for example, Navier-Stokes equations, okay, that's equations that describe fluid flow. And you can write down these equations, but you cannot solve them anymore. You can't find a solution. For a few toy problems there are now solutions, but they're really not the things you're interested in. You're interested in how the plane behaves when you fly. You're not interested in a totally artificial toy problem. So you can't do that. You need for your theory, you can't solve it anymore. Also, for some of the theory, you don't want to do the experiment. If you have an idea how you build a bridge, okay, you don't want to do a few experiments whether it actually holds. Okay? Or if you think about medical research, if you have an idea how to treat cancer, you don't want to make a few trials. Okay, you can't. That would be ethically inappropriate. For economic reasons as well. If you have an idea how you design your latest plane, you can't build a wind tunnel that fits a Boeing or an Airbus jet. Okay, you can only do it on a small scale. So there is certain things, constraints there. If you think about experiments, there's further things. Nowadays, you have such good sensors everywhere. They deliver such an enormous amount of volume of data, and it comes in with such an enormous speed, such a variety, and it's noisy. There is no way you can do that with traditional pen and paper anymore, okay? Or manually. Previously, we were standing in the lab, and we just kept spreadsheets of what we measure. It doesn't work that way anymore. So the solution is very simple. What we have to do is we have to use computers for those two things. We need machine learning, data analysis for the experimental side, and we need simulations for the theory side to cover that part. And then still that thing holds with forth and back. Now, this is, let me have a look whether I have a slide on that. If you study literature, you will see a lot of people who say there's actually now at least 3 pillars, and that simulation is another pillar. But there's also people who challenge that, who say, no. It's still theory and experiment. It's just we use computers for both of them. And I'm a little bit from that camp now. Okay, so theory and experiment. Okay, now there is bad news. This is, and you can open your laptop and you can look that up yourself. There's top500.org. That is a page which is updated twice a year, always in around May, June, because there's a big conference in Germany, which is called the International Supercomputing. And then it's updated once more around November. There's a big conference in the US, which is called Supercomputing. And what they do is they basically collect what is the biggest and fastest computer in the world. And this is on top 500, and you can look that up where the list is not up to date because for a couple of years now China refused to submit their computers. So we are pretty sure that there's some computers missing on that list. But in principle, it gives you a good idea what the trend is. And you can create this graph here yourself. That one is from 23, so it's totally outdated. But you can look at the top 500 list and you can play around with the data. And that thing shows you 3 lines. The one in the middle, that is the fastest computer on Earth. And you see it always jumps. You see those jumps? There, whenever a new computer comes online, you have this sudden jump. Okay? And you see, sometimes for a couple of years, so Fugaku, that was the Japanese machine, was there for quite a while, was the #1 machine. You have these plateaus, but you see that jumps. That one, down here, is the last computer that just made it into the top 500. That just got above the threshold. And this one here is just the sum of the performance of all of these machines. So therefore, those two, this one is very smooth because it's the sum. This one has here these jumps. So, and the interesting thing now is, you see this is exponential growth of speed. And then something happened here in that area. It flattens. Okay, so now let's go back. Has anybody here ever played Wolfenstein or Doom? These ego shooters, where, okay? So those were the first few first-person shooters. And when you spoke to the developers, well, in interviews, the developers said, that was 20 years ago, when they started to write a piece of code, they always wrote code which was too slow for the machine. So they had a certain idea, okay, we want to have that many monsters on screen, and we want to have that resolution, and we want to have that kind of scenarios in our game. And when they started developing, there was no computer who could deliver that performance. But what they did is, well, they said, well, we are here, we know this is when we want to release the game. So let's write code that's actually too slow or too demanding for the current machine, but we know by the time we're gonna release our game, we will just have the top-notch graphics and things like that. They use this thing. Okay? So another more scientific story, what you knew is you wrote a code at one point or a data analysis application, and you knew as the machine becomes faster and faster and faster, you will be able to use the same code a couple of years later and do way bigger and cooler simulations. Because you have compilers, you knew that you can automatically just retranslate, and you will benefit from that next generation of the next cooler computer, and you can exploit it. Now something happened here, and we can discuss that in greater detail later on. We call it the end of Dennard scaling. But what happened here is really that computers stopped to get faster. Because they're becoming too small and they consume too much power. And I think, well, most people think, that it will de-accelerate further. So we might eventually almost, well, this growth won't happen like that, won't continue like that. And this is also the point where computers started to flip, and you now use more and more GPUs, because GPUs are actually more primitive than CPUs. They're simpler, but they're more parallel. We discuss that later on, and therefore they deliver more performance per watt, per energy. That is really the selling point of GPUs. You get more performance for electricity cost. Okay? For these machines up here, we say after around 2 years, you have paid the same amount for your energy bill than for the computer. So they're very power hungry. Okay, so this is where we are. And this means, at this point here in that era, we didn't really have to care so much about the programming languages. We could just write our code, and it got faster automatically. And now, unless you were at the top notch. Okay, these people were always geeky and diving into their code. But now we have changed. We got back to a time where it makes very much sense to understand exactly how a programming language works, because you can't rely on your computer to automatically give you more performance. Okay, so what kind of what kind of programming language do we want? We always are kind of drawn in between those things. So we want to write more code, more complicated code, quicker. So we want to have a higher abstraction level. But due to this slower growth in performance, the problem is we need a lower abstraction level because we want to exploit those machines. So we want to abstract too much because we pay a price. So we permanently have to balance between those two different regimes. And there is one language which is very good for that, and that is C. So why do we teach C? Well, first of all, it's still one of the dominating languages on supercomputers. The other one that we could teach is Fortran. And I will give you evidence for that one in a second. The next advantage is C was developed originally hand in hand with Unix. And as you know, Linux is still the dominating machine for scientific applications, for servers, for big machine learning clusters. So C and Unix, they just fit together very well because everything was written in C originally. It is still C, C++ is still the backbone behind all fast Python libraries, okay? You might say, I do a machine learning code in Python, and it's a very high level script where you build your neural network. At the end of the day, the heavy lifting is done by C under the hood, okay? We discussed that with the interpreter and compiler. An interpreted language would be way too slow to do really high data analysis. Also very nice about C is you can think of it as the cousin or grandfather of CUDA. When NVIDIA introduced the CUDA programming language and paradigms, they didn't start from scratch on the green field. They wanted to have something that people immediately feel familiar with. So what they did is they took C and they added all the GPU stuff to it, and then it became a different language. But you see, they're very, very similar. Certain concepts are in both languages. So it makes sense to study C, so you can work on a very high abstraction level, but nevertheless, you can also work very, very close to the hardware. So when we teach you how to exploit the latest hardware for your case, we can do that in C. With Python, Java would be very more complicated. With C, we have the right abstraction levels. We can do all flavors of parallel, and that means today that is the way how you get faster. Okay, if the machines don't get faster anymore, you need more of them. With C, you can support all of that. And as I said, in particular C++, that is, we will see what C and C++ are in a second, that features all of the new programming paradigms that you might want to touch upon as well. So it's probably the language of choice here at the moment. Okay, I wanted to provide you evidence how important C is. This is kind of this company here, or this consortium, they have made studies how much language, what languages are used. And you see here the bright bluish line. This is Python. And you saw there was a little bit of a Python hype just after 2004. It went up. After that, people said, yeah, it's just yet another scripting language. And it kind of was here at around 5% plus minus of the codes used Python. And then you see this huge, from here on Python 2018, Python really took off. That is machine learning. Because most of the machine learning codes are written in Python. So now it's really Python is the most frequently used language. But that is due to machine learning, okay? That's due to one domain. Okay, then you have Java. Java was huge in the 2000s, okay? Every business rewrote all of their software in Java. It's still used, but you see there is kind of a permanent trend that goes down. That's okay. That happens to most languages. What else do we have? We have C#, which is kind of the Microsoft Java counterpart, and you see it is used, okay, but it is not that popular. I don't know why SQL and PHP are in there. I think they didn't fit that well. You see Visual Basic is here. Yeah, JavaScript, all fine. But the really interesting thing is C, that is black, and C++. And you see, they're more or less stable, okay? There are some dips in here. But you see also, together with the rise of machine learning, all of a sudden C and C++ are going up again. Because that is what most people use under the hood to write the really, when you need a lot of performance, when it is important, where it makes a difference how effectively you can use your machine, you have to write code that is close to the hardware, that understands that von Neumann principle, where you can do certain things, and that is the reason why they all again went up. So yeah, makes sense to study this language, even though it is very, very old. So in that context, we should probably revisit our course. The course is called Introduction to Scientific C++ Program. We have different titles, I think, for the course, but this is the message, okay? It is about how you do that for science and research. It is not how to build a web page in 2 days. We don't want to work on that level. We want to understand what is happening under the hood if we write C code. We want to understand, and if we have to, 99% of our time we don't have to, but if we have to, we want to be able to explain, if I write this down, what happens on the von Neumann level? What happens with registers? Where is data going where? This is kind of, we want to be able to do that if we have to do that. So we want to learn the behind the scenes. This is the objective of this particular course. C++. So I gave you a case why we want to use C. I hope I've convinced you that it's a good choice. The very moment you want to learn something about GPU, you will definitely understand that, yeah, this is the right choice. And I also gave you an idea of what the C++ language should do for us with the computer architecture. Okay, so the first thing is a big disadvantage, disappointment. Where does the name C comes from? Well, it's very simple. There's a couple of, well, these are kind of the inventors, godfathers, Ken Thompson and Dennis Ritchie of C, and what they did is they had developed something they called A, and then in 1970 Ken Thompson introduced something and he called it B, and then the natural choice for the next language that they invented was C, and there is a D indeed. I'm not sure whether there is an E, I don't think so, because the D never took off. Okay, so he called it C. Anyway, so what did these guys do? Well, they worked at Bell Labs at the time, okay, telco company, and they had to write an operating system, which you still use because they were working on Unix. Okay, and they found this very, very tedious and laborious and exhausting because they had to write a lot of it in assembler. Okay? So they didn't want to write stuff in assembler. So what they did is, well, they invented a new programming language. That's what I said before. Every real computer scientist invents a new language. Okay? That's exactly what they did. And they did that in 1972. And then it took them more than 10 years to actually make it, so people were using it all over the world, but it was actually not really a standard. It was nothing you could say, this is correct C, because it took them a very, very, very long time to actually make it standardized. Okay? Anyway, so what is C? Well, they had, what did they have in mind? They had a couple of things in mind. They wanted something that is close to the machine. Okay? Because it had to be efficient, they used it for telecommunication devices. Okay, so it had to be very, very small. It had to fit onto portable devices, like phones at the time. Had to be fast, but still, they wanted it to be very rigorous. So it had to be almost as fast as assembler, but easier to use. And this is probably the reason why NVIDIA chose it as the baseline for the GPU, because they want to have something that's almost as, by definition, doesn't introduce a lot of overhead. Okay, so that is C. It took them quite a while to get it off. It's still used heavily, in particular than CUDA. But it didn't provide certain abstraction levels that were en vogue at the time. So there was, for example, a language that's called Smalltalk, where you had different objects interacting with each other and speaking to each other, which was a very nice way to model big applications, and C couldn't provide that with onboard. So somebody came along and extended it. And in C, you can write, for example, a variable, which is something we're going to discuss tomorrow. But in C, you can write a variable, and if you want to increment it by 1, you can write a equals a plus 1. But in C, you can also write a plus plus. So if you want to introduce something that takes C and adds something on top, then Björn Strostrup here decided, oh, let's call it C++, because I take C and I add something on top. This is exactly what he did, by the way, originally. He played around with C and he added certain libraries on top of C, written in C. That was how he wrote the first C++ compilers. So, around 1980, there were a lot of new ideas, quite academic probably, how to improve efficiency. And efficiency here means how fast, how quickly you can write code, what kind of abstraction level you have at your disposal. And there were new languages there, but no one used those big new languages. A few people in academia at universities used them. But companies struggled because they had so much written in C already, and they had so many staff who were trained in C that they said, we can't just throw everything away and rewrite it. By the way, footnote, if you study Java, Java looks very similar to C++ for similar reasons, and I can tell you about that in a second. Anyway, C. So they wanted to have something that or Strostrup wanted to have something that has the cool new features, but you don't have to totally switch gears. And so he came up with that idea of C++, defined that one, and then around 85 he had his I/O library, how to write stuff somewhere, and then he got that finalized, and there was the first commercial implementation, so you could now buy a C++ compiler, and they had also a standardization. It wasn't really standardized at the time. What he did is he wrote a book. I have it in my office. It's a big one, okay? And if you ever read it, don't do it. It's really hard to read. It's not very accessible. But that was kind of the definition what the C++ language. It's just that book was for quite a while. And it has evolved. In 98, it was then finally standardized. So an industry body came together and said, this is C++. And now it has really changed gears. So now you see in 2003, they had a new version, then they had a new one in 2011, 14, 17, 20. So now C++ can do parallel programming here in the language. It can do functors. You're going to see that later on. So it really evolves. 23, and I think at the moment they're working on 27 already. Okay, so there is new C languages coming out. They add things to the original language. That's probably not so relevant for us. I just said Java and C#. If you look at them, and if you are not super familiar with C++, you will think, if you know C++ and you look at Java code or C# code, you will see that they look quite similar. And the reason is C++ was so successful, but people complained that it's too complicated. So what people said at IBM at the time, let's take C++, strip it of all the complicated stuff and make a simpler C++ with some new concepts, and they called it Java. So nerds say Java is actually C++ minus minus, because minus minus is reduces the number by 1. Okay? So Java, C#, very similar. And there is now extensions to that. So for example, if you've ever heard of Cycle, which is an open GPU programming language, that is again an extension of C++. And the newest C++, I don't think the 27th generation, but new C++ will also natively support GPUs at one point. So it's still evolving, and there is still a lot of variety there. Okay, so how do we write C code? Now we get a little bit more hands-on. Okay, now let's do something in C. And we're gonna need 3 tools. The first one is an editor. An editor is an application where you can write text. Okay, but it has to be a real editor, not Word or something like this. So I use VI. You can Emacs, Notepad, whatever you want to use, or you can use a whole environment like Eclipse or Visual Studio or whatever. At the end of the day, what you need is an editor where you write simple text files. You will call them .c or .cpp, but that is just convention. It has to be a simple text file, nothing else. Okay? This is your source code. Then you will use a compiler. We do that on the command line, and you can use GCC or G++ for C or for C++, for example. And this is really the thing we had seen before, where you take the where you take the source code and you translate it into machine code. And then depending on how many of your, you won't, on the long term, you won't work with one single file. You're gonna work with multiple different files. So what you also need at the end is a linker, which all bundles it together and gives you an executable, which you can then run. Okay? So these are the tools that you need: editor, compiler, linker. Let's have a look. Okay. So the editor, we've already said that. And now I make an analogy that we're going to use later on multiple times, or we can use later on. Think about you're preparing a meal. Okay, you're cooking. Then the editor, that is really where you write your source code. So it's kind of a recipe, okay, for a single dish. You write, this is how I do that. Do this, do this, do this, do this. It's a cooking instruction for the computer, which tells the computer exactly do this, and then this, and then this, and then this. This is what the text file holds. And typically we store it in a file which has the extension .c for C code, or has the extension .cpp for C++ code. But if you see it, it's really just a text file with instructions. Do this, do this, do this. The compiler then is kind of the thing that cooks the whole thing. So now we translate it into something that's machine code, okay? And the result is also called object code. And we will see that in a second. So we translate it. Again, if you take the cooking analogy, you take the recipe, you cook it, you have one dish, and the outcome will be a file with the extension .o. I'm going to see it in a second. And then what you need for a proper meal, you have to arrange all the individual dishes into your whole thing, and that is then the linker, which takes all the individual things and assembles them into one big application. Okay? And that gives you an executable. Okay. In later stages of this course, we're going to have multiple of these files when we have more complex code. So we have files that have the extension CPP, plain text. Nothing surprising. We're going to see one at the end of this course. We might also have so-called header files. This is something we will discuss later on. And now we say C++ for C++ code, or otherwise, for example, GCC. And by the way, as the C compiler and Unix were developed hand in hand, every single Unix or Linux installation that you have has always a C compiler, which is very convenient. If you did another language, you would have to install things. You don't have to do that on a Linux system. C is usually shipped with it. Okay? So we type in G++, and then we do -c, and then we give the file name. So for example, file1.cpp. This tells the compiler, translate it into machine code. And what you will get if you type in this, you will get a file that's called file1.o. That is an object file. You can do that for multiple files. G++ minus C file 2 gives you a file 2.0. And then you have a linker, G++, and now you give it all the object files. And that is wrong, that should be a -o, my apple, and then tells you, can you create me one executable, which you can eventually execute. Okay? So the important thing is compile, link it together, run it, which fits exactly to our compilation process. Okay, let's do that. This is now a first C++ C program, C. We're gonna see the difference between C and C++ later on. This is C, hello world. So if we type in that, and I will really ask you this afternoon, you should try that out. And it just says hello world on the terminal. That's the classic, you do that with every single programming language. Okay, this is plain, so all of this here is in a plain text file. I have used fonts here to give it different colors, but that's just for you to make it easier to see it. You won't see that on your editor, unless your editor has syntax highlighting. And this is very close to what a machine does. So forget about this. We discuss that later on. You translate this. So this is translated into machine code, and the corresponding machine code is dumped into the main memory. Okay, all of this. And then, again, we will discuss what integer main void here means. But what happens in the machine is that the program counter is now set to this point. And now the computer reads through it, and it jumps in here when you load it. The next thing it sees is called this printf, which is print file. So in Unix, everything is a file, also what you see on the terminal. Well, we discuss that line later on as well. It says hello world. And then return 0, that means it terminates. Okay? But this is the simplest C program you can think of. And as I said, every single ingredient here will be discussed in future sessions. Okay, so what do? We can type in GCC, and again, this is something you have to do today, and then that's basically everything you have to do for today, and then you're well prepared for tomorrow. You type in GCC hello world.c -o hello, and what this does is it takes hello world.c and translates it into an object file, but then I have not passed in a -c, so -c says please compile only. I have skipped that part, so what this means, it says, okay, then I have to compile and link immediately afterwards. So it takes this one, translates it into machine codes, and then produces an executable, which I call hello. And on a Linux terminal, I have to type in dash, and I execute it this way. And what you should get out then is you get a hello world, and then you have written your first ever C code. It's as simple as that. Let me wrap up what we have discussed, just for you to see. And then please ask me any questions after that, okay? So we have introduced the von Neumann architecture, and there were 4 ingredients. The ALU, which does the calculations, arithmetic logic unit. There is something we call the memory, that is where both the application and the data are stored. We have a bus which connects those two, and we will see why that causes issues. And we have a control unit, which is kind of the mastermind keeping it all together. So this is a schematic idea of what a computer looks like. We have discussed that thing with the memory versus registers. Registers are these sheets of paper in the office where you do the actual calculation. The memory is where the actual big data starts, and we have to move data forth and back. Again, we're going to see how this causes major headaches in modern applications, but this is how we compute the machines. We have discussed the difference between assembler versus high-level programming languages. And I hope I've made the case why it is important that we use the productive high-level languages where I can do a lot of cool stuff very quickly. But you should still, nevertheless, you should always understand what is happening under the hood. So we have assembler versus high-level language like C, C++. And we have quickly discussed the difference between the interpreter and the compiler, clarifying that we work usually with a compiled language here, whereas if you do Python, you always work in the interpreted scheme. I've shown you the top 500 list just to flag that we are now in a real dilemma at the moment. On the one hand, we want to use the high abstraction levels, and actually we want to have even higher abstraction levels, something like neural network domain-specific languages, what we have with PyTorch and TensorFlow. But at the same time, to make progress, we need the low-level efficiency, and we permanently have to balance between those two things. Programming efficiency versus program efficiency. We have discussed the workflow. We edit a file, we compile it, we link the whole thing together. That is how we produce an application. And I've given you the Hello World code. And that's everything for today. So thanks for dropping in. Thanks for dialing in as well. And I'm happy to take questions.